The work is in high energy physics, but I decided to give a review which is accessible to people who are not in high energy physics, other areas. That's kind of an important notion. Generally, symmetry probably has other applications, in particular in condensed matter physics. But as a result, those of you who are from high energy physics probably won't hear anything new in this talk, which I apologize for. So, okay. So symmetry is an important organizing principle in physics. It was first recognized, well, probably in the first one in the 19th century, actually, and not by physicists, but by crystallographers. And they were the first to apply group theory to physics, even before the notion of a group has been defined. But more recently, because people like, say, Einstein, in effect, recognized some important new symmetry of nature, and that's often led to breakthrough. You could say that, say, people like Copernicus, Galileo, Newton established invariance under, say, Galilean group, and then Einstein improved it to Poincare symmetry, and that's an important insight that all the laws of physics are invariant under this symmetry. Now, when you discuss classical mechanics, then what is this? Symmetry is simply a transformation of variables, which is invertible and takes, which gives equations of motion unchanged. Well, typically, we also require a bit more. We require the symplectic form on the phase space to be unchanged. The quantum analog of this is also pretty simple, at least in quantum mechanics. So symmetry is a unitary operator in Hilbert space, which commutes with the Hamiltonian operator. The unitarity is the basic analogous to unitarity in the quantum case is analogous to preserving the symplectic form in the classical case. So in commutation with the Hamiltonian is equivalent essentially to leaving equations of motion unchanged. From the definition, composition of symmetries is again a symmetry. And every symmetry has an inverse by definition, because we wanted an invertible transformation involved. Every unitary operator has an inverse. So symmetries form an abstract group. So as I already mentioned, the relevance of group theory to physics was understood by 19th century crystallographers who used it to classify all possible crystalline structures. Explicitly, the relevance of a Poincare group to physics was realized by Hermann Minkowski, who, well, Einstein didn't think in these terms, but Minkowski recognized there's a group there which preserves a symmetry, which includes Lorentz transformations. And later, when quantum mechanics was discovered, then Eugen Wigner especially showed how useful it is to apply group theory to physics, especially theory of group representations. Now, I should stress that when I say symmetry, talk about symmetries, I'm talking about I'm not talking about gauge symmetries. Gauge symmetries are different from symmetries which we so far discussed, because they act trivially on observable quantities. They don't do anything to observables. So what are they for? Well, they arise when one uses a redundant set of variables. Of course, it's desirable not to have redundancy, but sometimes it's unavoidable if you want to ensure some other nice properties like locality. For example, diffeomorphism symmetry in general relativity is essentially unavoidable. If you want to have a local description, you need to carry around this diffeomorphism gauge symmetry. Interestingly, when Maxwell wrote his equations, he also used the non-gauge invariant quantities. So the potential, the vector and scalar potential. Later, and that's part of the reason his equations were so complicated. First of all, he didn't use vector calculus, what was before vector calculus was invented, essentially. And second, he used components, so he can use components, but also he used vector and scalar potential. That was like horrible. And then later, Oliver Heaviside rewrote Maxwell equations using gauge invariant non-redundant quantities, E and B, which he introduced. But sometimes that doesn't work. So in an abelian gauge symmetry, it's crucial to have a local description of the standard model. So there's no way to rewrite standard model using gauge invariant variables only. So it's all old hat. So what's the new thing? Well, in quantum field theory, it looks like combining locality with symmetry leads to a much richer notion called higher form symmetry. The usual symmetries, of course, are a special case, and then usually referred to as zero-form symmetries in this context. But there are also symmetries with p-form symmetries, where p is greater than 0. And mathematical structure, which this generalized symmetries form, is not simply a group. It's actually what's called a homotopy type. I'll discuss what this means. So that's actually an important insight into the mathematical formulation of quantum field theory. I think that's probably the most important result. It's philosophical result that whatever quantum field theory is, and it has not been rigorously defined mathematically, its symmetry should be this much more complicated notion, homotopy type, or maybe even something more complicated if you care about some like so far I'm just talking about generalizing what an abstract group is. But if you want a generalized notion of a Lie group, then it needs more defined notion than homotopy type, which I will not mention. Anyway, so and another important lesson from this development is that low energy physics of condensed matter system often contains emergent higher form symmetries, even though typically you don't have microscopic higher form symmetries. People also consider even further generalizations, non-invertible symmetries, for example, and subsystem symmetries, but I will not talk about those. So what's the new idea? Well, let's start with the path integral formulation of quantum mechanics. Suppose we want to have some transformation of variables, which upon quantization becomes a unitary operator. And the transformation I'll call F. So matrix element of a unitary can be presented as some path integral. The integral is over all trajectories, which have discontinuity. Like if you don't have discontinuity, that's just a matrix element of evolution at all. Without just identity. But if you do have discontinuity, then of this particular kind, that is, as you go from t less than t naught to t greater than t naught, then the variable q changes to its transformation under the symmetry. Well, that represents in the path integral language matrix element of u. Now, if u is really a symmetry, then this matrix element actually does not depend on t naught. You can change the discontinuity, location of discontinuity in time, and the matrix element does not change. So in that sense, very simple, you can interpret it saying that symmetries are represented by topological defects, so discontinuities in the field variables. Now, if you look at quantum field theory, well, now instead of a q, you have now a variable, some sort of phi, which depends both on time and space. X is a collective variable for spatial coordinates. Now, you can still consider symmetry transformation at a time slice by some value t naught, and you still have a defect, sort of discontinuity in the which corresponds to action of the unitary, and its effect on the correlation function does not depend on t naught, because again, if it's really a symmetry, then shifting t naught is the same as conjugating with the evolution operator, and that actually goes, that doesn't change locally. However, in quantum field theory, we can deform the defects in a more complicated way, not just simply move it up and down in time, but do some more violent deformation. And we can ask, are correlators unchanged under such deformations? That in principle does not follow from the fact that this defect is a symmetry. So to make life simpler, let's look at continuous symmetries, which are more familiar. So, and I say that the symmetry is locally acting in the sense that if there is a local conservation law such that the unitary is obtained by integrating a current, well, the time component of the current. So the unitary is defined like this. By definition, it is some conserved current, which you can whose not component insert here and define a unitary. And this depends on some parameter alpha, which is parameterize your transformation. It's a one parameter kind of. It's basically your group in this case is simply a real line on U1. Now we'd like to define an insertion of U on any hypersurface, just like in the previous slide. Now, what do I mean by inserting U on this general surface? Well, by definition, we say, well, it's the following thing. It's exponential. In the path integral, you insert this thing where n nu is a normal to the dimension or to the hypersurface sigma. And you still have the parameter L. So that's the definition. And then now we're asking whether it's topological defect in the path integral. And actually it is, precisely because you have a conservation law for J. The path integral can easily verify does not change under deformations of sigma. So more precisely, the same sigma prime the same homology class by Stokes' theorem in conservation. So we conclude that what they call locally acting symmetries in the quantum field theory are indeed the invertible topological defects of per dimension 1, where you reach dimension, the defects in dimension d-1, where it leaves dimension of space-time. Now here we have like an obvious generalization. Why don't we allow sigma to be just the surface of some dimension d minus p minus 1, where p is some parameter must be greater or equal than 0. And this is what we did in this paper with David De Gaiotto, Nadia Seiberg, and Brian Willett in 2014. So in a paper called Generalized Global Symmetries, sometimes called also higher symmetries. So higher meaning that p is strictly greater than 0. So, and again, by definition, we say that if you can define this defect for sigma of this dimension for some fixed p, so that the path integral does not change under deformations of this surface, and the theory is said to have a p-form symmetry. And you still require this this defect to be invertible, so there's an inverse defect. And okay, so these p-form symmetries greater than 0 are called higher symmetries or generalized symmetries. And the usual symmetries have p equals 0. Now, okay, so okay, what does it imply? Well, it implies well, first of all, we can ask, okay, is there some notion of a current for a higher form symmetry? In the continuous, well, this notion makes sense only for continuous symmetries. We have them for zero form symmetries, and we also have them for p form symmetries. So for p is 0, actually, even though people usually say that the current is a vector field, it's actually better to think of them as a d-1 forms, because then conservation is simply this equation. So your d-1 form is being closed. That's a very natural formulation because the well, the usual current is a sort of Hodge dual of this, essentially Hodge dual of this form. So the natural thing about this is that if you have the hypersurface, this submanifold of dimension d-1, you can just integrate a d-1 form over it once it's oriented. In conservation, also much more easily written in this language. Now, if you have a d-p-1 manifold over which you want to integrate something, then you need a d-p-1 form, and the conserved current is simply a closed d-p-1 form, that is the one which is filled by the de Rham operator. That's what the current is for p-form symmetries. It's actually helpful to look at the Hamiltonian viewpoint, and for simplicity, I'll look at the case p equals 1, the first non-trivial case. So we're assuming now that space-time has this form, some space times time, and we decompose this current d-2 form into a d-2 form on the space and a d-3 form, which really comes from the mixed components, time-like and space-like ones of the d-2 form. So in terms of these two pair of forms, conservation equation looks as follows. We have so this is sort of charge density, and its time derivative is exact, that is d of some of the sigma. But in addition, you also have this equation, something which you don't have in the p equals 0 case. It just says that the charge density is a closed two-form. So yeah, in the case equals 0, that's automatic, because in that case, the row. So, but here it's a separate part of the conservation. So conserved charge is obtained by integrating this d-2 form over, well, you have a spatial manifold which is d-1 dimensional, so you need some 1 form to wedge with this d-2 form to get a d-1 form. So the parameter in this case is a 1 form. And if you ask what's needed for this one form for it to be conserved, for this Q of alpha to be conserved, well, you can easily check from this conservation equation. Well, that this guy is is time independent, provided alpha is closed 1 form. So in the for p equals 0, the parameter was a constant, but for p equals 1, the parameter was a closed 1 form analysis by. This is actually the name, the origin of the name, 1 form symmetry in this case. And similarly, for p greater than 0, the parameter for transformation will be a closed p form. Now, you say, wait a second, the space of closed 1 form is infinite dimensional. So do we have infinite number of parameters then? Well, actually, most of these give trivial charge. Namely, if alpha is d of some function, well, it's the same in the case p equals 1, then the charge corresponding to such alpha is actually 0. Such alpha is called exact. So why is it 0? Well, because we have this extra conservation equation. The charge density is a closed with this 2. So non-trivial 1 form symmetries correspond to the quotient of the space of closed 1 forms by the space of exact 1 forms. And this quotient is called the first de Rham cohomology of a space. So now the dimension of this space, of course, depends on the topology of this manifold. But anyway, in the end, it's, well, but usually for most, typically it's finite dimensional. So so space of parameters is actually finite dimensional, just like for ordinary 0 form symmetry. Let me give a couple examples. First of all, in Maxwell theory, in 4 dimensions, if you don't have magnetic charges, which is normal case, then you have you have a 1 form symmetry whose charge is a 2 form. It's closed because it's topologically, because F, basically the fact that divergence magnetic field is 0. Now, if you also don't have no electric charge, then you have an additional 1 form symmetry in the same thing. Its charge is the Hodge dual of this F, and the current is this, and the charge is this electric flux. These are examples of 1 form symmetries. In general, well, examples with other well, and here's an example or series of examples of other p form symmetries. If you look at the scalar field in the dimensions, which is periodic, then it has a d-2 form symmetry. And corresponding current is actually 1 form, simply the derivative of the field. And the charge is the winding number. Now, what structure do higher form symmetries form? Well, first of all, if you collide two parallels of defects of dimension d-1, you get a new defect of the same dimension, and the labels must be composed according to some consistent rule, which means that you get a group, which let's call this group GP. It's a group of p form symmetries. For p greater than 0, this group is necessarily abelian. Why is that? Well, if you have p greater than 0, then defects of codimension 2, you can braid them in space-time, so they never overlap, but the time ordering is reversed. So you have this commutativity. So unlike ordinary symmetries, higher form symmetries all commutative. Now, so far I've been talking about continuous symmetries. What about if the symmetry is discrete? Well, then you cannot talk about local conservation law. Instead, you have to define a discrete symmetry to be locally acting if its defect can be promoted from flat to arbitrary in such a way that it's topological. So we have some topological defect. Whenever you have topological defect, which does not change when sigma is deformed, you say you have a and these defects are labeled some discrete label, so you have a discrete local acting symmetry. So actually, almost all discrete symmetries which occur in practice are locally acting. So, for example, in the lattice formulation of symmetries, it's very clear. So if discrete form symmetry is an abelian group G, so then its defects simply have a label which carries this element of G. Now, the fact that defects are labeled by elements of some commutative group G doesn't mean that unit transformations in the Hamiltonian picture are labeled by these defects. We already saw that, say, for continuous symmetries, what labels unitaries is not the group G itself, but for continuous symmetry with one parameter, what labels unitaries is degree P cohomology of the spatial manifold. In general, when you have some group G, not just the one parameter group, then the unitaries depend on both G and the topology of this manifold. So let's look at what these unitaries are labeled by. So, okay, so first of all, if you allow only arbitrary defects, then it's natural to consider also network of defects. In order to be able to draw pictures, I'll focus now on the case when we are in a three-dimensional space-time, and the symmetry has p equals 1. It's a one-form symmetry. So then space is then two-dimensional, so I can draw pictures on a plane. So that's spatial slice. Okay, so I'm considering networks of defects of, well, they're codimension codimension 2 in space-time, and imagine that they are extended in time direction. So codimension, so they're actually lines in drawing this line in the plane. So they inserted at a fixed time, and they also look like one-dimensional things in the plane. Now here's you have this flat pieces of defects labeled by some group elements. Now this is and they merge in some way. It's actually convenient to think in terms of a slightly different way. One can say cover this space with charts, and the fields undergo a transformation in this group when going from one chart to another. So if you think about this way, well, let's use a picture of charts. So this is the one chart, which called W3. To the left, we have another chart called W1, and above this line, I have a chart called W2. So the locations of the lines, then sort of in this picture, well, here drew some particular lines, but the defects are topological. So it shouldn't matter too much how I drew them. That sort of makes it explicit. So here I first chose charts, and then I can also draw lines in double overlaps of these charts if I want to, but I don't have to. Now if you look about this picture, then it's to say, well, if I go from chart 1 to chart 2, and there goes a transformation F1, 2, and then from chart 2 to chart 3, another one, given by some other element of the group, then I better have consistency. So then I must have this. If I go all around, this will come back to the original variable. So if we go back to this picture, it means that the product of these three elements, appropriately oriented, should be 1. That's a consistency condition or networks of defects. Now, further, the local nature of symmetry, its local action, means you can deform and actually reconnect the network without changing the unit. And this leads to an equivalence relation on consistent labeled networks of defects. So different networks correspond to the same unitary operator, may correspond to the same unitary operator. If you try to formulate mathematically what it means to reconnect the network, and if you rephrase it in terms of this regions W, you'll find that consistent networks, equivalence classes of consistent labeled networks is precisely what mathematically called the check cohomology. So of the manifold D-1. So we conclude that unitary transformations of equiform symmetry are labeled by elements of this check cohomology group, which physically can think of it as equivalence classes of consistent labeled networks. It might seem a bit strange, but this actually generalizes the case P equals 0. In that case, P equals 0, this is just a G itself for connected dimensional. now it's a good time to give some examples of discrete higher symmetries. Well, first of all, you have the center symmetry, famous center symmetry of SUN-Yang-Mills theory. If you formulate Yang-Mills theory in four-dimensional spacetime, it's not an ordinary symmetry, but it's a one-form symmetry, ZN one-form symmetry. And the conserved charge in this case is what's called its hooked electric flux. If you look at SUN mod ZN Yang-Mills theory, it's a different Yang-Mills theory, closely related to this one. Then this actually has another symmetry with P equals D minus 3. When D is 4, it actually also is a one-form symmetry. And we get actually one-form symmetry just as in the like in this case. But they're no longer realizing the same theory. If you want to have magnetic, if you want to have electric symmetry, then you need this gauge. If you want to have magnetic one, you have a different gauge. You don't have them at the same time. Another example is abelian anyons. This corresponds to P equals 1. These are defects of codimension 2, so they're precisely correspond to P equals 1. What are conserved charges? Well, in this case, they're string operators creating any. So normally can be deformed, and these are precisely topological defects. Well, why abelian? Well, it's simply because we decided, well, we wanted invertibility, right? So our string operators would have an inverse. If you don't impose that, then you could say, well, non-abelian anyons correspond to non-invertible symmetries that the one considers. Now, so far, considered only defect networks in space, but you can also consider them in space-time. So far, my defect networks were just local, all attached to some particular time, all to some fixed time slice. But you can also consider them just in space-time. Their interpretation is different. Like take ordinary symmetry. In this case, equivalence classes of defect networks, the same way as before, correspond to now elements of degree 1. Why 1? Well, because now they have codimension 1 in space-time, right? So you place space with space-time, and instead of 0, put 1 because in space they have codimension 0, but in space-time they have codimension 1. So what are these things? These are flat gauge fields for the group. So when you put defect network in space-time, that's just coupling the system to a flat gauge field. And it remains true even for P equals 0, but now the gauge fields live in this group. And that's just high-form gauge field. So high-form gauge fields were extensively discussed in the context of string theory, topological field theory. So it's what was new in our work from 2014 was the interpretation of some things as global symmetries. One can also let P equals minus 1 in some cases. For example, well, with P minus 1, you cannot do it for unitaries, but for these networks, you can consider, you say, well, H0 of space time definitely makes sense. Okay. What is that? Well, just a set of locally constant functions from your space time to this G. And to define this, you don't even need G to be a group. You just consider just G to be any set. If you want to consider P minus 1 symmetries, that just they're labeled not by group, but just by sets. So this is sort of a pattern. The higher P is, the more structure you have. For P equals 0, G is a commutative group. For P equals greater than 0, P equals 0 is any group. For P equals minus 1 is actually any set. Well, so basically, what we conclude from this is that P minus 1 gauge field with values in a set G is a discrete local parameter for monofield theory. And this parameter just takes values in this set G. So, okay, so that suggests that perhaps one should try to interpret this for P arbitrary P, the same thing. This group of, the group of defect, which labels defect networks in terms of maps from XD to some other space. When P equals minus 1, these are literally maps from your space-time to the set G. And we can also try to interpret this group for general P in terms of maps from XD to some space. What is a space? Well, it turns out that for any commutative group, at any P greater or equal than 0, there is some space called KGP plus 1, such that the set of equivalence classes of continuous maps to the space is actually the same as that thing. So actually, it's the type of the P plus 1. And that space is actually, well, can be taken the same for all space times existing. What I mean when I say set of equivalence classes, I mean that the maps equivalent is a homotopy, can be deformed continuously into each other. So in other words, a gauge field for T-form symmetry is simply the same as a homotopy class of maps from X to this space. Well, this space is actually quite, this space is what the spaces are first introduced by mathematicians Eilenberg and MacLean in the 1940s. They're not really spaces because they're not uniquely defined. They're just defined up to what's called homotopy equivalence. You say that space Y is of type KGN if all homotopy groups of Y are trivial, with exceptions of the nth one. The nth one is equal to G. Turns out that, okay, this doesn't determine the space Y uniquely, but determines it up to some equivalence relation called the homotopy equivalence. What do the spaces look like? Well, here's a simple example. If S1 is of type KZ1, because its only homotopy group is the first one, and it's equal to Z. But typically spaces of some type KGN are infinite dimensional. Say if you just look at KZ mod 2, what's an example of space of this type? Well, it's you can take, for example, infinite dimensional sphere divided by the antipodal map, the map which identifies opposite points in the sphere. The case P equals 1 is special because G actually can be non-abelian. In this case, this space is usually denoted BG, or the classifying space for G. And the cohomology of this space is called the group cohomology of G. Okay, so now we have this interpretation. Let's go back and ask, okay, what does it mean to reconnect? So we discussed that reconnecting network in space of spatial defects, which are localized in time, doesn't change the unitary at all. Now, reconnecting the network in space-time is interpreted as a gauge transformation of the gauge. Now, of course, it's good when the path integral is invariant under this reconnection, or maybe, but sometimes it's only invariant up to a phase. And that means that gauge invariance, strictly speaking, is violated. In this case, you say that, well, you could, of course, there's some leeway on how you define defects and their junctions. You maybe try to restore gauge invariance, but if you cannot do that in a local way, then you say you have a 't Hooft anomaly. So this is a notion of a 't Hooft anomaly for global symmetry, or zero form symmetry. But you can naturally generalize it to higher symmetry simply by considering networks of defects of higher codimension. If you reconnect the network and path integral does change by a phase, you say, and you cannot remove this phase by simply redefining the defects, then you say you have a 't Hooft anomaly. It's interesting to classify all possible 't Hooft anomalies, and it's currently believed that for a discrete group, at least, any 't Hooft anomaly can be cancelled by anomaly inflow from a topological gauge in one dimension pi. So this is a sketch of proof by Thorngren and Wang fairly recently, but there's no mathematical rigorous proof still, because actually, well, there's some substantial complication because there's some so-called mixed gravitational gauge 't Hooft anomalies that makes things complicated. But if you neglect those, then you can show that the anomalies in dimension d plus 1 are given by this, the anomalies in dimension d, again, typo, given by elements of hd plus 1, with u1 of this Eilenberg-MacLean space with u1 coefficients. In particular, for p equals 0, zero form symmetry, the 't Hooft anomalies are classified by group cohomology, homology of this classifying space of the group, which is simply KG1 of degree d plus 1. Actually, for D2 or less, it was known since 1980s in the context of conformal field theory. And for perturbative Fulton anomalies, a similar result was known since 1970s. But for high dimensions and non-perturbative anomalies, that's an important new result, which is again partially conjectural because we don't really know how to account properly for mixed gradation anomalies. Consider a three-dimensional. As an example, consider. How much time do I have? Okay. So okay, so here's an example. If you have three-dimensional TQ of T, as already mentioned, it has one-form symmetry given by abelian anyons in the form commutative group. Now, networks of abelian anyons are not topological because of non-trivial braiding. So therefore, one expects Fulton anomaly is just determined by the braiding. And this is discussed recently by Xin, Lam, and Cyber. And so that means that if you decided to gauge this one-form symmetry, then you cannot actually gauge any subgroup because you want to have gauge invariance. You only can gauge that subgroup of the group of abelian anyons which have trivial braiding with each other. So that's well, gauging such a subgroup is called condensing anyons. Now, even more interesting math arises if you look at how interact with different P. So if you just ignore all symmetries except particular P form symmetry, then there's nothing to talk about. It's just the group structure. But suppose you have several symmetries for different values of P. For example, if you have SU3 anneals theory, it has, of course, this one-form symmetry, which I already mentioned, whose charge is whose electric flux. It also has an ordinary zero-form symmetry called charge conjugation, and that negates electric flux. So they don't actually commute with each other. That's a very simple example, but it illustrates that different P's can talk to each other. So what sort of structure does it form in general? Here it's simply sort of semi-direct product, but that's a very special form of interaction between symmetries with different P. The general case can be only understood using homotopy theory. What's that about? Well, so we say that space Y is homotopy equivalent to space Y prime if there are continuous maps to directions such that compositions of these maps can be continuously deformed to identity maps of Y and Y prime respectively. And you say if the spaces have the same homotopy type if they're equivalent in this sense. In particular, if you already mentioned, if the space has a single non-trivial homotopy group, then its homotopy type is uniquely determined. So we call KGN. But if you have two or more non-trivial homotopy groups, then just knowing this group does not determine the homotopy type, precisely because of interaction. And homotopy theory tells us about all possible ways this can happen. So that just illustrates, suppose we only have two non-trivial symmetries, zero form and the one form. So this G is general, this is commutative. Now, homotopy theory tells us actually this the most general homotopy type of this sort, where first homotopy group is G, and the second homotopy group is G prime, is a fiber bundle whose base is KG1, that is classifying space for G, and the fiber is this one. So here's like a picture of this fiber bundle. The base is the fibers. And such fibers can be classified up to homotopy equivalence, and you can express the answer in terms of group theory of these two groups. And part of this data is an action of G on G prime, but it's not all there is. In the example which I gave, that's all there is, but in general, there's some additional data which determines how this guy is fiber to the base. So in general, if you have a P form symmetries for more than two values of P, a group theoretic description, like I just sort of sketched, it becomes horribly complicated. It's better to work directly with the homotopy type. And here's a reasonable conjecture that symmetry of quantum field theory in dimension Z is described by a connected homotopy type with non-trivial homotopy groups of P up to the dimension of spacetime. So in the case of quantum mechanics, these ones, so all you have is a KG1, the simple homotopy type, with a single homotopy group. So it's equivalent to specifying this guy is equivalent to specifying the group G. But in general, you get this complicated structure, and here's the slogan: topology is a generalization of symmetry. More precisely, homotopic topology. That's the right thing for quantum field theory. And that's actually important. We still don't know what quantum field theory is mathematically, but that's an important piece of information. Whatever your definition of quantum field theory is, it should make sure that symmetry is actually a homotopy type, not just a group. I should mention some about charged objects. If there are charges, should be charged objects. Well, ordinary symmetry acts on local observables. So if you have some local observables, some point, how they act? Well, it's surrounded with a defect, and you get a new local observable. Now, one-form symmetry similarly acts on line observables. So a line is surrounded with a defect of codimension 2, and you get a new line observable. Thus, p-form symmetry acts on p-dimensional observables. I'll skip examples. Well, Wilson loops, for example, are charged under electric one-form symmetry. Hooft loops are charged under magnetic one-form symmetry. So there are these examples. So these are non-topological sort of line operators charged under p-form symmetries, which correspond to topological defects. Now, in the abelian anyons, an interesting case, because abelian anyons themselves, in TQFT, define observables, define generators of symmetries, topological defects, but they're also charged under the same one, under each other. So that's precisely, in fact, an abelian anyon can be charged under itself. So that's precisely the phenomenon of braiding or Hooft anomaly. So whenever a defect is charged under some other defect, that means you have a Hooft anomaly. Now, one important subtlety is only a defect with a topologically non-trivial support can have non-zero charge. So, so more precisely, if you have a charge defect, it must be supported on a manifold, which defines a non-zero element in the homology group of your spatial manifold. Well, here jihad is the characters for drag and dual. For example, if you have a Wilson loop, then to have non-zero charge on the electric one-form symmetry, strictly speaking, it must wrap a geometric loop, which is not a boundary of a surface. In particular, when its loop wraps a thermal circle, then you call it Polyakov loop. In that way, notion of one-form symmetry is related to the center symmetry familiar from Young-Mills theory. You can do many things with the high form symmetries. You can do with ordinary symmetries. For example, you can ask if they can be spontaneously broken. So the usual diagnostics of breaking of a symmetry is that, look at the two-point function of some charged observable, and you find that the two-point function does not become zero, even if it takes separation very large. That's such a local observable called an order parameter. And contrary-wise, if all such correlators for all charged local observables decay as x goes to infinity, that means that there's no spontaneous symmetry break. And you can try to generalize this definition to arbitrary p. You just need to replace local observables with observables supported on p-dimensional submanifolds. So, for example, let's look at Young-Mills theory with group SUN. So you have one-form symmetry, charged things are Wilson loops, and well, strictly speaking, charged. Strictly speaking, it's the take Wilson loop to be topologically non-trivial, but let's replace it. Just take a circle of one, and then typical behavior is like this: you have a perimeter law or area law. Perimeter law, well, corresponds to spontaneously broken symmetry, while area law, because of this rapid decay, interpreted as unbroken one-form symmetry. Traditionally, the first option corresponds to Coulomb or Higgs space, while the second option corresponds to confining phase. So So in this way, you can distinguish at least the confining phase from these two phases using an loop-like autoparameter. So you can so you can rephrase spontaneous symmetry break. Well, confining phase is a phase with unbroken symmetry, and the other two is phase with broken symmetry. This does not distinguish Coulomb from Higgs phase. Now, another interesting application of this notion of one-form symmetry is that the following. So Yang-Mills has a parameter called the theta angle. It only affects non-perturbative behavior, it's so difficult to study. It's called the theta vacuum angle. Now, another difficulty is that while we know from Monte Carlo simulations that Yang-Mills theory in 4 dimensions is gapped, in fact, trivially gapped, in confining for 0 values of parameter, and hard to tell what's happening for non-zero values of parameter. It's difficult to numerically simulate because of this sign problem, essentially. Now, in this later paper with Zohar and David and Nadia Seiberg, we argued that at theta equals pi, halfway between 0 and 2 pi, either CP is spontaneously broken, or the theory is not confining. And the argument uses precisely a Fuft anomaly between one-form symmetry and the CP symmetry, and show exists in this theory. So a Fuft anomaly gives some more info of high-form symmetry, gives some interesting physical information. And you can use the same anomaly to constrain the behavior of Yang-Mills theory at positive temperature. Finally, I want to talk a little bit about emergent higher symmetries in condensed matter systems. In condensed matter models, you actually don't have macroscopic higher form symmetries because the point is that all observables are simply products of local observables. And local observables cannot be charged on the higher form symmetry, so nothing non-trivial can happen. However, low energy effective field theory can have emergent Gauss laws and then emergent higher symmetries. That is, in emergent effective field theory, you can have non-local observables, which is not simply products of local observables in the effective field theory. So emergent symmetries cannot be explicitly broken by local terms in the effective Hamiltonians, but actually they become exact symmetries of the low energy field theory. This is important. For example, suppose you have gap ground state, energy gap between the ground state and the excited state. Then you can say that a higher symmetry of the ground state is simply, it is a symmetry of the low energy description. In this case, it's usually topological planar field theory. So any higher symmetry of the ground state is a symmetry of the low energy effective field theory. An simplest example has been known for years for the toric code model. So that's a very simple model into the lattice. On each edge, you have a spin half degree of freedom or qubit, and you have two terms in the Hamiltonian products over Pauli matrices attached according to the vertex, like 4 Pauli matrices according to the 4 edges, and terms according to plaquettes, product of all Z Pauli matrices around the particular point on the dual lattice. So this model has unique gap ground state and infinite volume, and in fact is described by topological quantum field theory at low energies. And well, if you literally look at this toric code, it has a huge symmetry. There's lots and lots of symmetries which act, but most of them act trivial in the low energy theory. After equation by this trivial symmetry, you have still left something. The something is Z2 cross Z2 one-form symmetry. What are generators? Well, just strings of X's along a path on the dual lattice or strings of Z's along a path on the original lattice. Now, this one-form symmetry is only present in low energies, so it's emergent. It's spontaneously broken because these loops do not exhibit. If you look at charged objects for this, then they actually do not exhibit area law. And moreover, turns out that the strings which generate electric Z2 actually charge on the magnetic Z2, vice versa. So that means you have a Fuft anomaly. And its properties ensure that CQFT is non-trivial, don't be trivial. That's important because imagine you start with a simple integrable Hamiltonian, which I already showed. Well, previous slide, but imagine deforming this Hamiltonian while keeping the gap open. Well, that deforms the theory, but it cannot change low energy behavior. If you're going to stay the same because you cannot do anything with the piaform symmetries. So that's an important point that that this notion of piaform symmetries is useful in condensed matter physics because it extends so-called Landau paradigm. Landau paradigm is a continuous phase transition due to spontaneous symmetry breaking. So you can classify phases by looking at symmetries, which symmetries are broken or not broken. Now, unfortunately, there are many exceptions. There are lots of phases and transitions which cannot be explained in terms of this simple Landau paradigm. For example, a trivial phase and topological order phase are different phases, but cannot explain these things, the difference in terms of symmetries, ordinary symmetries. So this transition between a trivial phase and a symmetry protected topological phase is also not part of Landau paradigm. But on the other hand, some of these cases can be associated with spontaneous breaking of p-form symmetries. In this way, higher symmetries enlarge the range of applicability of Landau paradigm. Of course, still there are lots of transitions which cannot be explained in terms of breaking of any type of symmetry, of piaform symmetry. Landau paradigm doesn't cover everything. And well, this suggests you should look for even more general notions of symmetry, like non-invertible symmetries, subsystem symmetries, and I was trying to extend the Landau paradigm even further. This corresponds, for example, subsystem symmetries is similar, but it do not require defects to be fully topological. Also.
These transitions, singularities of log Cn divided by n equals to infinity. Phase transitions. Log Cn divided by n equals to infinity. Singularities.
No, I just meant that you change parameters in the Hamiltonian.
Yeah.
And you start with a situation when there's an energy gap in the spectrum, then you change parameters, then the gap becomes zero suddenly, and then, well, not suddenly, but at some point, and then once you pass that point, you have a totally different phase with different properties, physical properties, but again, gap. This is an way phase transition.
Some broken symmetries, right? But in some much more details.
So I'm just saying that sometimes typical phase transition, most like canonical one, most like standard one, when you have a parameter and there's a change on one side of, say, for positive value parameters, the symmetry is unbroken, on the parameters less than zero is broken. Now, we just start considering more general situation when some piaform symmetries can be broken and broken on two sides. That allows to incorporate more phase transitions into this picture for Landau.
So do we only consider the closed informal symmetry? We also consider
Yeah, so that precisely has to do with topological nature. Like if you relax being topological, you don't need to consider, well, okay, so different situations. You can consider, for example, non-topological symmetries, like subsystem symmetries, or you can consider gauge. Well, if you relax if the generator is not a closed thing, not a closed form, that means you're looking at non-topological symmetries. If your parameter is not closed, that means you're gauging this. So these are two different things.
Why the non-topological effect that is a subsystem?
Well, I mean, just can consider symmetries which act on some particular location. It's rare, it's unusual to have such symmetry, but you can consider them. They have the same property as piaform symmetries because they act only on degrees of freedom. Well, there's some associated with circles, right? Dimension in space where the symmetries act. In that sense, they're somewhat similar to piaform symmetries. But the analogy is it's just an analogy. nothing deep. Yeah, it just so you have different symmetries. It's more like a gauge symmetry in some sense. It's closer to gauge. It's kind of halfway between gauge symmetry and global subsystem symmetry.
Is feature.
Well, I mean, you can have, say, some subsystem symmetry, which is partially topological, say. So there are lots of things you can consider there.
So you mentioned this higher form symmetry breaking area law versus this parameter law. So what is the transition? What's the product? And also, in the case of, I would expect there would be probably some power law, but in the case of parameter law, probably I would also expect that there's some long-range correlation happening on the planet. I don't know how to distinguish this from transition between this symmetry breaking.
Well, I can't really say. All I can say is that you can use this perimeter law versus area law to distinguish different gap phases, or different, say, gap confining phase from another phase. What happens in transition, I don't know. This is that doesn't help in talking about high form symmetries. It's a dynamical question, so I'll stay with it.
You mentioned the phase transition from a trivial phase to a topological ordered phase. We understand that you with a higher symmetry form.
Well, in general, high form symmetry is not going to be relevant, but in the case when topological phase is abelian, let's say, well, it's a transition where emergent high form symmetry is spontaneously broken. For example, a transition to a toric code phase can be thought of as a transition where emergent high form symmetry is broken. It's kind of similar to, say, the liquid vapor transition, where you have an emergent Z2 symmetry, and you interpret the transition as a transition of the critical point is the where the liquid vapor equilibrium ends. The critical point where the liquid vapor equilibrium line ends is often interpreted as a point where which separates a broken phase with a broken phase. And the symmetry in that case is zero form symmetry and the Z2 symmetry. But that symmetry is not a microscopic symmetry, it's just an emergent symmetry. So you can similarly say that transition from a confining phase of, say, Young's of a Z2 gauge theory in 3 dimensions to toric code phase, with the confined phase, is similar. It's a transition from the unbroken emergent Z2 symmetry to broken phase. Very similar to critical transition in 3 dimensions.
And not Kapustin, yes.